Hello, my name is Daniel Hellstrom, and I'm representing Frontgrade Gaisler from Sweden. So it's midday, and in Sweden it's midnight. So let's do this. I'm going to talk to you about the software ecosystem updates that we do for our next generation microprocessor, the 765. So we consider ourselves a world leader when it comes to creating embedded computer systems for harsh environments, and we design fault tolerant into the computers and into our hardware IP that are used to develop SOC systems. Which we then manufacture into standard components using radiation-hardened technologies. The same hardware IPs can also be used by ourselves or our users to design custom FPGA solutions or even full custom ASICs. In our IP portfolio, the most important IPs are our processor IPs that are the Spark Leon or the RISC-V Noel 5 new processor. Together with this, we also have a software ecosystem to be able to use the processors. Looking at our portfolio of microprocessors, we have a long heritage of Leon processors in white, which are available on the market. Those have some different properties in terms of processing performance and interfaces and so on. And in orange, you have the new generation that is currently in development for both Spark processors, and we are also introducing RISC-V to our portfolio. And all our systems are purpose-built for space. This is our current generation, our most high-performance microprocessor at the moment, called 740. It runs at 250 megahertz, and it has been manufactured at ST65 nanometer technology, and it's a Spark 32-bit machine. So this is how that architecture looks like. It's a quad-core computer where the processors are attached to one single processor bus and then connected to L2 cache of 2 megabytes. And behind that, there's an SDRAM controller. Then it also has, of course, a couple of I/O interfaces like SpaceWire router and CAN controllers, 1553, PCI to extend with external FPGA for more functionality, and Ethernet. If we look at our next generation SoC that is currently in development, we have listened to our users and feedback on the 740, and this will come in a larger package, which has much more pins, and thus we don't have to pin multiplex as much as before. The target frequency is 800 megahertz, and it will be a octa-core machine, and it's manufactured in ST28 nanometers technology. So this is a block diagram. It's kind of messy. There's a lot of functionality, and I've taken out a lot of slides and try to focus on the software parts later on. But so this is an octa-core machine. It can run in either Spark or RISC-V mode. And by a pin at bootstrap after reset, you can control if it will enter Spark or RISC-V mode. This comes with a lot of new functionality in terms of interfaces. We have the same set of interfaces as we had in the 740. It's just that those have been upgraded. Instead of on 2 CAN, we have now 4 CANs. Instead of one 1553, we have 2 1553. And then there's a lot of new high-speed interfaces. Space fiber, for example, which is also integrated to the SpaceWire router, so you can communicate through SpaceWire into space fiber without touching software. There's a Ethernet switch featuring many more Ethernet ports than before, and we're also developing for PCIe into this SoC. So the previous generation had Leon 4. Now we're introducing Leon 5. The main difference there is that it is a dual issue machine, so it can execute 2 instructions per clock. But this allows you to reuse your software easily because it's a Spark. If you have used 740 or other Leons before. But we have also done other improvements, such as the fault tolerance features. The other alternative, the RISC-V, Node 5, it's about the same processing performance as the Leon 5. It's also a dual issue pipeline. This introduces 64-bit ISA to our portfolio. And a lot of other functionalities within security, for example, and also hypervisor extension. So we have faster interfaces, which pumps data in and out much faster, higher performance, processing performance from the CPU cores, which means also that we need a faster interconnect. So instead of having one shared AMBA bus, now we have 4. And the addresses of the I/O or the CPUs then determine which AMBA bus is used or accessed. And each of those AMBA buses have a dedicated L2 cache. And behind the L2 cache is a dedicated DDR memory port. So the DDR controller has 4 DDR ports, which then is optimized and generates a good, utilizes the DDR modules as possible. So this is transparent to software. You can use it without knowing this. On the other hand, you can also leverage this by, for example, determining which addresses a CPU or a set of CPUs access. You can create isolation between the CPUs. You can probably imagine that. But we also have some configuration options where we can control which addresses actually selects the AMBA bus, which AMBA bus. So looking into the software, we have some ongoing development activities. This we have been running this activity, ESA activity, in 2 years now. So it's coming to an end, where we have had a focus on Leon 5, and we have focused on 3 software components. The GR boot flight bootloader, where we have ported to Leon 5, and at the same time also updated to new specification and made other improvements to all of these components at the same time. The T-Sim simulator has also been updated for 765 and Leon 5. Same goes with Linux. We added new device drivers, and I've been researching into a way to leverage more than 4 gigabytes of memory. This activity is a bit larger, also an ESA activity where the focus is on RISC-V instead. In this activity, we have 11 different development tracks. So we try to cover 11 different software components. Again, we have TSIM development, where we extend for the simulation tool for RISC-V and NOL5. And also bootloader, and on the compiler side, we try to describe our new compiler dual issue pipeline to do compiler optimizations. And we're also looking into third-party development tools so that other vendors can support our processor with tools. And also, again, looking at Linux support, and we have some research topics looking into containers, running them on NOL5 and real-time simulation systems, and also boot authentication. And on RTEMS, our focus has been on device drivers. So we are developing device drivers according to the ESSS E40 and Q80 standards, similar to DO178. So that's the main focus there. And there's, on the left side, you have a list of device drivers that we have been focusing at. And okay, I think this is the previous version of the slides, but okay. So looking into the software releases which we have done lately, we've updated GCC and GDB into the latest versions into our tool chains last year. And on the Linux side, we've our main focus has been to improve the 740 Linux support. So typically board bring up, we have focused on simplifying board bring up. So watchdog device drivers, clock gate device drivers, pinmax drivers in the ecosystem. So it's not only the kernel, but also this first stage bootloader. It may seem a bit simple, but on the watchdog side, we have had to go into the architecture of Spark to find good places where to kick the watchdog. And also we've looked into the initialization of memory. So now larger memories are also, the boot time is significantly improved. We have our annual updates of build root, and then we've also merged the NOL5, the RISC-V packages that we have into the same releases as Leon. So now we only have one software package for both processors. So it's much easier to use. And we have released part of the what we have developed in one of the activities I mentioned. So now we have a 765 support out there in our packages, and the wider address support that we put develop effort in is now available. So we can use more than 4 gigabytes of RAM by using the Linux HiMem support. Looking at more recent releases here is from one of the activities, we've looked into authentication of boot images, where the bootloader would then authenticate and verify the integrity of an application image before it's booted, and if it's not okay, then it will step to the next. So this is mainly a documentation release to have a platform for our users to provide feedback if this is a good product, and if it's a solution that is working for the customers. So this is a pure software solution. And we also have a working prototype for 740 that comes together with this. So if you're interested in that, you could talk to me or contact us and we have a evaluation that's possible to get. So we use that to also benchmark the boot time when we have this authentication turned on. 716B software ecosystem has now been released for our new microprocessor. So a large part of that has been GR4, which is our hardware debugger. So that's a new version that released in January. The major feature is the 716B and the support for the RTA processors that's included in that microprocessor. But also 765 support is now available in GR1. And RISC-V improvements and so on is going into that. There's also a new license model as a subscription available. On TSIM, basically the output of one of the activities we have now released in March, where this can be used as a GR765 software development platform, but it can also be used to measure performance or analyze your application. Since 765 isn't available yet, we have done the development and compared against FPGA prototypes. So of course you can also get FPGA prototypes from us, but this simulator offers other functionality as well. So in the project we have focused on the architecture, like I mentioned before, the striped buses and split it up the L2 caches and the Leon 5 interconnect to that. But a lot of time has also gone into developing detailed models of the Leon 5 processor model. So now we are able to model 2 instructions per clock, and also branch prediction unit and pipeline effects and all sorts of things. So this has been developed on a 765 prototype, so it's not the design is still evolving. So of course we need to update this in the future, but it's very useful as it is. In green you have the models that we currently feature and the white ones is where we are lacking models. But it is able to run Linux, for example, on VxWorks and Artems. We also use this to run validation and unit tests on our bootloader. So this is our next release for April that we plan, and it will be our bootloader GR boot and standby that we release with 765 support and Leon 5 configuration. This bootloader has been designed according to the ECSS, E40 and EQ80 again. We have made some improvements to the software architecture of the bootloader at the same time. And we've updated, so we're more compliant to E40 and Q80, and we've tested this on FPGA prototypes and validated on that. So same goes with as the simulator. Once the 765 silicon is available, of course we need to revalidate and so on. But still, that's it's good that we have that available already now. And also a third-party partner has done independent software validation and verification of this product. I sometimes get questions on Linux support and preempt RT. So I just want to mention that we have been at a slow pace working on looking into this. And you probably heard that preempt RT has now made it into the kernel since October. It's not supported by Spark in the main line, but we have spent some time on that, and also ESA has also done work which we have collaborated with ESA on, and so we have a high resolution timer driver now available for all the Leons, and we are preparing to release a beta for this in October. And in the meanwhile, we're setting up a demonstration using our, the Frontgrade SPC8 single board computer. We're using that platform to demonstrate this real-time, the improvements for real-time. And that was my last slide. Thank you.
Any questions?
Hi, I'm wondering if you can share with us any performance analysis results you have in comparing all else equal RISC-V with Leon 5. For example, some performance maybe CoreMark versus FPGA LUT, or CoreMark versus milliwatts of power.
Okay, on power. No, I'm not sure I have any power figures. There might be available on our homepage, but for this particular, for the 765, we have some CoreMark and Drivestone figures here, and on the RISC-V, there's at least a CoreMark figure.
Thank you. There is a question online. Does the TSIM3 support GDB integration?
GDB? Mm-hmm. Yes, it does. And also this new architecture in TSIM. I mean, now that we've done the modeling of the architecture, we also, as I said, we also implement RISC-V support in TSIM. So we reuse that part of the architecture and add a RISC-V model, a processor model to TSIM, and also the user interface has to be updated. So that will be available late this year, more on functional modulation and simulation.
Thank you. Any more questions? We can take one more.
Thank you for your presentation. I'm interested in, let's say that the trend right now that we would like to incorporate AI and also high processing power thing into the our space application. What is your plan or your vision on this?
On
the AI and machine learning.
AI, good question. So as I said, I haven't included all the presentation material for the 765, but there are some extensions for in the RISC-V that's planned. Maybe I can show you if you swing by our booth.
I think we can take one last question.
This might be a little bit of a simple question, but when you mentioned that processor is like space qualified or rad hardened, what is the actual process to determine that?
We build in fault tolerance by design by adding mechanisms to detect bit flips or preventing bit flips. And then if it happens and it can't be corrected, then the processor would detect that, and you may get a trap or exception or similar. Then that's on the hardware design. Then on the technology that is being manufactured, there's a whole level of different mechanisms to protect from various upsets or so. So there's also the packaging plays a role. So it's really the whole design flow that has to be taken into account.
Thank you very much, Daniel.
Thank you.